Hello learners, welcome back to the course on deformation processing of materials. In the previous lecture, we had seen the effect of stresses and mainly the residual stresses on the formed part, and after that we had seen the stresses required for drawing. Also, we had seen the effect of friction in case of drawing, and we also later on considered the effect of inhomogeneous deformation and accordingly modified the equation for stress required. Then we calculated a numerical, and after that we started the metal forming process known as forging. In that we had seen the drop forging process, press forging process, etc. And we had seen the volume consistency equation. We also saw that uh, the potential energy increases as we rise or raise the hammer so as to carry on the forging process. And again, we revisited the concept that the pressure which is applied by ram is not uh, exactly transferred to the workpiece. In fact, the force remains same. And if we want to calculate the pressure, we need to consider the surface area or cross-sectional area of our specimen. So, as I had mentioned, now we will begin today's discussion with the advantages and disadvantages of forging process, and we will see later some further parameters related to this. Okay, so let us see the advantages of forging process. Advantages of forging process. Okay, so basically the forging process refines the microstructure. Okay, so it is one of the advantageous thing. So this refines the microstructure. Forging refines the microstructure. Okay. Now the next one is that uniform structure is formed or obtained after the process of forging. So it produces uniform structure. It produces uniform structure. Okay. Porosity gets reduced, so less porosity. Less porosity is obtained, and a variety of shapes and sizes can be formed using the process of forging. So, variety of shapes and sizes can be formed. Okay. Also, the machining which is required after this process is very less. So, okay, before that, in fact, the shape and sizes you can correlate, with an example, like the wheels of railways and large gears, etc., are made using this process only. So, railway wheels and large gears, etc. Large gears are made using forging. made using forging. So this was an example for this advantage. Now next I told was less machining. And also the production cost is relatively lower. Okay, so it saves production. Next. Okay. So these were some advantages. And as we know, everything cannot be only advantageous. It would have some limitations also. So there are certain disadvantages also. So the disadvantages of forging process. Forging process. Okay. So what could be the disadvantages here? Here, control over dimensions is difficult. It is a tedious task to maintain or to obtain the very precise dimensions. Okay, so it is difficult to achieve close dimensions. Difficult to achieve close dimensions. Next one is initial cost is very high because we know that this is a cheap process, but the initial setup requirement uh, needs very high expenses. Okay, so initial cost is high. Initial cost is high. Other thing is there are chances of cracking of the workpiece. Okay, so cracks. Again, the maintenance of equipment is costlier. Okay, because there are very big hammers, etc., which uh, if fail, then it would lead to very high cost to repair them. So maintenance cost is high. Maintenance cost is high. And again, in case of hot forging operation, the material which are at higher temperatures would be directly exposed to atmospheres which are uh, which may be corrosive for them or which may lead to oxidation of the surfaces. Okay, so this is a potential threat in case of this hot forging operation. So in hot forging, and generally we adopt hot forming operation only because they require lower stresses. So in hot forging, rapid oxidation of metal surface due to high temperatures, due to high high temperatures. Okay, so these were certain disadvantages associated with the forging process. So Let us see a very quick example related to the volume consistency. Although it is very simple and you would have gained very good control over this concept as we have seen it frequently, but let us revise that. So say we have a question in which in open die forging, we will see what is meant by open die forging and closed die forging in a while. Open die forging. We have a suppose we have a cylindrical workpiece like this. Let me draw it more clearly. Say like this. Okay. Its initial diameter is say 200 mm. 200 mm, and final diameter is 60 mm. Not final diameter, actually height. Height is say 60 mm. And assuming there is no friction between the surface of this workpiece and the forging dies, the final diameter, and only we are given with the final diameter, okay, after forging. Now we need to calculate the final height. This can be easily done using the volume consistency equation. Okay. So say after forging this becomes 400 mm. Okay. So what is the final height? This we need to find. So simply we can apply the volume consistency here and we can get the final height. So how will it be? Simply let us apply d naught square, initial diameter square into, okay, let me write the entire thing by volume consistency. We have pi by 4 d naught square h naught is equal to pi by 4 df square hf. Okay. So we are given with the values of d naught, h naught, and df. We need to find hf. This pi by 4 get cancelled out. So we have this hf as d naught square h naught by df. Okay. So simply let us substitute the values. So upon substituting, this comes out to be, this was 200 square. Everything is in mm. So let us keep as it is without changing the units. So we get the height also in units of mm. Okay, so this was h naught 60 and this becomes 400. Okay, so this is also square, 400 square. So upon solving this, we will get HF as nothing but this will be again 40,000 upon into 60 upon, this will become 16 and this 1,60,000. Okay, so this cancelled out, gets cancelled out. Okay, in fact, this cancels out and here it remains as it is. So finally this comes out to be nothing but 4 times and this 15 times. Okay, so this is 15 mm. In this way, we can implement the volume consistency equation. This was a very quick numerical. Again, we had seen that when we raise the hammer, its potential energy gets increased. So later, when this hammer is dropped and it hits the workpiece, this potential energy gets converted into work which is utilized in uh, the forming process or this forging operation. And ultimately, this work itself leads to the deformation and uh, reduction in height of the workpiece. Okay, so let us understand or see this with the help of another numerical, which will include this concept again. Okay, so now this is, say we have a hammer and we have a workpiece. Okay, so let us say this is the workpiece we have, and from here we go to height capital H. So say here we have the hammer. Okay. This is the hammer, and this height is say H. Okay. So what happens here is the change in energy we have seen delta E is nothing but mgh. Okay. Where h is this height, m is the mass of hammer, and g is the acceleration due to gravity. Okay. So, and say the initial thickness of workpiece is h naught, and after deformation it becomes hf. Let me write that also. So h naught is initial thickness and hf is the final thickness. Okay, and say F is the force which is applied onto the workpiece. Force applied on workpiece. And again, we know that sigma F bar is the flow stress of the workpiece material, and A will be the area of cross section, final cross sectional area of the forged material or forged part. Okay, so here what will happen is uh, by the concept of this energy getting converted into work, we can equate the work. Work is nothing but force into displacement, and displacement here will be the change in thickness, how much the thickness is getting reduced. Okay, so force into that displacement delta H. Delta H will be H naught minus HF, because this is the change in thickness. Okay, so this will be equal to delta E. Okay, or this say F delta H will be mgh. So here delta H is H naught minus HF, and this F is flow stress into the final cross-sectional area. Again, this sigma F bar we know that is given by K epsilon to power n over n plus 1, which is nothing but the average flow stress. Okay. Average flow stress and this AF is nothing but the final area. Okay. This is like this. And again, remember the volume consistency equation is applicable here also. So d naught square h naught will be equal to ef square hf. Okay. So based on this, let us see a numerical. So we have the given data. Okay, so we are say given with initial thickness is say 100 mm, and after forging this becomes 70 mm. Okay, so and also the flow stress is given to us. It is the average flow stress is 100 megapascals. We are also given with the initial diameter, and this is 150 mm. Okay, and also we are given with the values of mass of hammer and acceleration due to gravity. Okay. So see if I've written it or not. Let me write it here that here m is mass of hammer and g is the acceleration due to gravity. So in this case, this mass is given as 2000 kgs, okay, or 2 tons we can say. So this is 2000 kg. Acceleration due to gravity we have to consider as 10 meters per second square. So we are given with this data. Now we need to find the height up to which the hammer needs to be raised to get this much reduction in the workpiece. Okay, so for given data, find h. So how can we approach this? So we can simply apply the equation we have seen earlier, which is F into delta H, which is equal to mg capital H. For that, delta H can be simply written as delta H is nothing but H naught minus HF, which is 100 minus 70, that is 30 mm. So we now have the value of this delta H. Now F we had seen was sigma bar into AF, and for AF we need to find the final diameter. So we will need to apply the volume consistency equation again. Okay, so now I'm directly applying the volume consistency. So this is d naught square h naught is df square hf. Okay, so upon solving, we simply get this df value as root over d naught square h naught by hf. And upon substituting the values, this df comes out to be 150 square into 100 by 70. Okay, and this comes out to be 179 mm approximately. I've already calculated this. So this becomes 179 mm. So let us call this as equation 1. 1. This is second. Now after this, we can now calculate the force. So therefore the force will be sigma F bar into AF, which is nothing but the sigma value is given to us as 100. So this is 100. And again, since this is in megapascals, so we can put the area in mm square and we will get the value of force in Newton directly. Okay, so this 100 into area is pi by 4. dF we calculated as 179. This is in mm square again. So on calculating this, force value comes out to be approximately force is nothing but this is around 25 lakh 24,373.24 newtons. Okay. So this much force we are getting, which will be applied onto the workpiece. Say this is equation number 3. Now again we can apply the relation. This F delta H is mg capital H. Okay. So let us put the values here. So remember this delta H we have calculated in mm, and when we will put it here, we'll need to put it in meters because everything we are putting in SI units. Okay. So here let us substitute the values one by one. So F came out to be 25,373.24. Delta H will be 30 into 10 to power minus 3 as it was in mm. So now converted into meters. And this mass was 2000. G is 10 and H we need to calculate. Okay, so this H becomes nothing but this product comes out to be 75731.20, and this will be now divided by 20,000. So 20,000, and again solving this, we get the value of H as around 3.79 meters. So this is the height up to which the hammer should be raised in order to reduce the thickness of 150 mm dia cylindrical rod or workpiece by 30 mm. Okay, which had the initial height or thickness at as 100 mm and finally it got reduced to 70 mm. Okay. So this is the way we can calculate the height required. So now let us see the effect of friction on this forging process. So till now we have considered that there is no friction between the die and workpiece. So there was homogeneous deformation and the diameter was getting extended as the height was getting reduced. Okay, so now we are seeing the effect of friction. Effect of friction. So when there is no friction, In case of no friction, what happened is, suppose we had the die and we had the workpiece like this. So upon forging, simply the height got reduced and the diameter got increased. This is die. This is the workpiece, or simply work we can call. So this got transformed like this. Okay, simply the diameter increases and height reduces. This is homogeneous deformation. Homogeneous deformation. Here friction is negligible, or no, in fact there is no friction, and force simply comes out to be sigma f bar af, as we have seen it earlier also. Okay. But what happens if there is presence of friction, or there is some friction between the dies and workpiece? So when the dies will try to compress the workpiece or press the workpiece, uh, the surface which is in contact with the dies will not be allowed to flow easily. Okay, it may not expand, or means it will not flow properly, so as to maintain the consistency or homogeneity. So due to this fact, the central region which is free to flow of the workpiece, let us consider a cylindrical workpiece. So central portion will easily flow out, whereas the upper portion and lower portion which is in contact with the dies will be restricted to flow, and they will not flow that much. So a barrel type shape will be formed. This effect is known as barreling. This is also observed in the case of compression test. If you would have seen this also. Okay, so barreling is also observed in case of forging. Okay, so in case of friction, in case of friction, so say again, this is our die like this, and here the workpiece is placed like this, and now here there is some friction. Okay. Here also there will be friction. So what happens in this case is, this material now, the diameter gets increased slightly, but not to the full extent. It should have uh, increased. Okay, so let me draw it properly. So this type of, what is happening here is, so a barrel type shape will be formed here like this. This becomes our workpiece now. And say, let me draw the dies to make it easy to visualize for you. So say this for the dies. So due to friction, barreling effect is observed. Okay, so here the coefficient of friction was not 0. Say it is 0.1. Okay. So here in the relation of force, we now need to incorporate the contribution of friction also. So here now the force equation becomes factor Kf into the flow stress into the final cross-sectional area. Okay. Here, Kf is the forging shape factor. Okay. This Kf is forging shape factor, and it is given by relation, which is here how it here, so it is clearly visible. This is given by 1 plus 0.4 times mu into df over hf. Okay, so you are very familiar with these terms, that mu is the coefficient of friction, df is the final diameter of the formed product, and hf is the final height or thickness. So substituting this kf into the relation number, we can get the value of force. Okay. Now let us see what are the various forging operations called, and what is open die forging and closed die forging. So let us see types of, or simply let us write open die and closed die forging, because these are the only two types here which we will be focusing on. So open and closed die forging. So open die forging is the simple forging operation which we have seen in the schematic also, that uh, that the workpiece is simply placed on the lower die or table, and it is pressed or hammered with the die from above, or we can also call it as punch, which is compressing or pressing it. So it is open to flow in the lateral direction or transverse direction, and it uh, forms or reduces the dimensions and forms the product. So here basically very close dimensions are not uh, possible. Okay, we cannot reach the accurate dimensions in open die forging, because material may flow to a larger extent or to a lower extent. Okay, so this is a process which forms to close to the final desired shape, but it is difficult to achieve the final dimensions. Whereas in case of closed die forging, the dies after joining with each other form closed cavity, into which the material after flowing gets restricted into the cavity. Okay, so very close tolerances or close dimensions are achievable. Basically, we can say that the final dimensions are achieved in closed die forging. Okay, so cavity basically is closed by two dies, two halves of the dies, and into that the material flows and fills the entire cavity and achieves the final desired shape and dimension. Okay, but there will be some defect or problem also in case of closed die forging, that uh, if we keep on pressing the material or forging the material, it may fill the entire cavity, but at certain places it will flow in excess. Okay, and in between the packing or the gap between the dies, it may flow out also. So that portion will be known as flash, and it is a sort of defect. Also, we should not call it a defect actually, because it may be beneficial also. It is actually beneficial also. In it basically acts as a buffer zone where we can keep the excess metal, so that the cavity gets filled properly. Okay, so open die forging is the simple process where forging is carried out between two flat dies. Okay. Open die forging is carried out between flat dies or dies of simple shape or simple shaped dies. Okay. Here, this process can be used for forming a very large number of components in a short time. Okay. And where the means very rapid production can be achieved. Okay. So open die forging, open die forging is adopted when lower number of components are to be formed, are to be, let's say, produced. Okay. And as I mentioned, that closed die forging is used to go to very accurate or close to the actual dimensions of the final product. So generally, this open die forging is used to form or pre-form the material for closed die forging. Means the component is forged in using the open die forging, and later it is subjected to closed die forging to get the final dimensions. So open die forging is many times used to preform the material for closed die forging. Closed die forging. Okay. So this was something for open die forging. Again, as we discussed that uh, in closed die forging, the workpiece is again forged using two dies, but it will have some cavity which will be closed, which will be having the dimensions of the product, and after forging the material takes the shape of cavity finally, which is uh, which leads to final shape or final accurate dimensions. It will be not exactly same to the original one, but very close to the original dimensions can be achieved here. Okay, so again in closed die forging, closed die forging involves dies which have a closed cavity okay. And very this is generally done under very high pressures. It is, so this was for open die forging. Open die forging. This we are seeing for closed die forging. It is done under high pressure. High pressure. Okay. And very close dimensional tolerances can be achieved here. Dimensional tolerances. Okay. So this is something for closed die forging. And again, as I had mentioned about the flash, due to that effect or phenomena, this closed die forging is in fact known as impression die forging. Okay, because uh, actually the material is in fact formed using closed die system or closed cavity system, but part of it flows out in the form of flash. So it basically is done like a impression, means the closed cavity impression is uh, given or is means carried over to the metal workpiece. Okay, so this is known as impression die forging in fact. Okay, so now let us see some of this forming forging processes. Okay, so how they are called based on the type of operation carried out. Okay, so let us see now various forging operations. Various. There are certain terminologies or names which are given to the process based on type of uh, dies used or type of loading, etc. Okay, so various forms of forging. So the very first basic process is known as edging. So let us see how edging is done. So edging is basically, let us see edging now. Okay, so edging. This is basically a process of reducing the dimensions of uh, ends of the bar, or not necessarily reducing the dimensions, giving them a different shape at the end, or the end of stock is given a particular shape through forging. Okay, so how is it done? Basically, there are dies. So let us say we have dies like this. Like this. Like this, we have the dies. And here the workpiece is fed into this cavity. So it was like this. Okay, so this is fed here, and these dies are pressed together. Okay, one may be the stationary one, and above one may be uh, attached with the hammer so that it strikes. Okay, and what happens after the closure? That the ends take the shape of the cavity of die. Okay. So let us say after closing, how it will appear. Let us say. So, suppose these were the dies. Okay. They will now come closer to each other, and will take the shape here like this, and the workpiece will now be like this. Okay. So it would have now, say this is like this. It now fills the die cavity and takes the shape of this die. So, somewhat like this. Okay. Let us say these were some thing like this, so that it gets closed at this end. So again, now the die will get closed here. So this process is known as edging, where edge of the stock has been given a particular shape using the forging process. So this is edging. Now the other process which comes under this forging operation is fullering. Fullering is used to reduce the central cross section of any component. Say we have a rod and we want to reduce some of the portion which lies in middle or in this towards the center. Center means like suppose a rod, say a rod is like this, this, and we want to reduce this section. Then in that case, fullering operation is carried out. Okay, so second one is fullering. So how fullering is done? Let me draw the dies and set up for this. So, say we have dies like this. Okay. And a similar arrangement will be at the towards the bottom like this. And this. What happens to it? Okay, so this is the arrangement of die, and when it gets pressed, if the workpiece lies between these two dies, basically the region which will be at this point is, so let me change the color. From here, the material will flow outwards towards these cavities, and the central portion of the material will get reduced. So one of the applications of this kind of process is the forming of, or yes, the forming of connecting rods of IC engines. Okay, so there you would have seen, or you can search on the internet how a connecting rod appears. So there the central region has reduced cross section as compared to the ends. So this fullering operation is used to form that kind of shapes. Okay. Because after pressing, the material will flow towards these outer cavities and get reduced in the central region. Okay. So next process is this is known as drawing. Basically, we have seen that drawing is a different operation, but this type of forging is also known as drawing. Basically, these two are correlated. If suppose there are two dies, okay, and they press the material and it is allowed to flow or pass between them, which leads to the change or reduction in cross section, then this is one type of forging, as it has similar application of loads which are used in forging operation. So the dimension gets reduced in between or in the center. So say we have drawing, how it appears. Suppose we have dies like this. Okay. And these are used to press the material like this. And suppose this is my workpiece. And from here it gets reduced in cross section. Okay. So this particular type of operation is known as drawing. Okay. Here the material is now getting reduced in cross section. And these were convex dies which were pressing the material in this form. And suppose the shape of these dies is changed to concave type. These were convex dies which were continuously pressing the material as it was passing through. So this is drawing. And if concave dies are used to reduce the dimension of material, suppose again this is a rod, and if we press it using concave dies like this and this, concave shaped dies like this, so that process will now be called as swaging. Okay, we had seen or the term swaging in wire drawing also. It meant the same there, that material was being used pressed using hammers or forged using hammers to reduce the dimension. So in swaging, concave dies will be used. So next one is swaging. Okay. So how now let us see the die setup for swaging. This is very similar to that of the edging dies, but edging was done like my material is coming like this, and edging was to reduce the end only. Okay, but in swaging it will be pressed across the section itself. Okay, so suppose my material is like this, now it will be pressed in the section. In edging this was pressed at the end, but in swaging we will be pressing it like this. Okay, so in swaging, say we have concave dies like this. And here again like this. And here comes my, I've drawn it a little bigger. The workpiece like something like this. And it is rotated and dies keep on pressing it. So this process is known as swedging. Okay, so these are various forms of forging operations which are done to achieve a different type of reductions in dimensions or uh, changes in cross sections as per our requirement. Okay. So with this, we have come to the end of this forging operation also. Now we have covered most of the metal forming operations that we encounter. So we will close this class now. In the next class, we will see quickly see the forming processes like bending and stretch forming, etc. And after that, I think we will reach towards the end of this course also. So at the end, we will see some uh, high energy rate forming operations and some of the severe plastic deformation operations also, if the time permits. Okay, so let us close for now. Thank you.